All right, page 219 in your textbooks. Page 219 in your textbooks. We've been working a lot with math lately. The handout that you were assigned for homework that's due tomorrow is pretty much all math. Today, we're going to take a little bit of break from math. We're going to do all proofs. So I give you some proof practice. You will have a proof on your test coming up Friday in lesson 151. Just one proof. But most of the test, of course, will be math, and tomorrow will be an all-math day. But for today, we're going to look at some proofs. And page 219, there's two sections, section 4.15, section 4.16. We're going to start in that top section. And go ahead and read number 4 for us, if you would, Chris.
AEB is a diameter, and DEF, any chord perpendicular to AB. Another chord AC cuts DF at K.
And so we are proving that.
Prove AB times AE equals AC times AK.
Good. At your seats, think through the picture. If you need to, reread it. Draw the picture. I will help you with this. The center of the circle is not E. That is not the center. E is any random point on the diameter. All right, hopefully you started with a circle. How many began there, drawing the circle? Drew a diameter, called it AB. Now, point E, I told you, is not necessarily the center. In fact, we need to assume it's not. We could either put it closer to A or closer to B. Quentin, what did you do with E? Closer to B. All right, so I'm not going to put like real super close to B, but maybe right about here. Pick a point, call it E. And E is simply the point through which we must draw DEF. And we need to draw DF perpendicular. How many had, wherever you picked E, doesn't really matter, but you drew a chord through E perpendicular to AB and called it DF. How many had that other chord? Excellent. But we're not done with the picture. There's a little bit more that needs to be drawn here. Ethan, what else needs to be drawn?
Chord AK.
Chord AK?
Chord AC.
Chord AC. Now, chord AC must start where, Ethan?
At A.
At A. And it could either go above AB or below AB. You chose to make it go above AB. All right, and we drew a chord, any chord, and, well, not any chord, because our chord AC had to intersect DF, so it couldn't come anywhere up here, had to cross DF at what point?
K.
Point K. How many had a chord AC, either above or below, doesn't matter, that cut through DF at a point K? How many of you had this picture, again, where the chord either went above or below? This chord was either one side or the other. You had the picture. Questions on how to get the picture? Fix the picture if you don't have it yet. Again, it doesn't have to be above. Your picture has a little flexibility there. And let's write down our given here. Let's go ahead and name the circle. Genesis, what would you like to name it? O. All right, so given circle O with the very first thing we drew, of course, Genesis, was a diameter. So given circle O with diameter AB. I'm too lazy to write the E. So I'm just going to say with diameter AB. The next thing to do is a chord, and it's not just any chord. If it were any chord, I really wouldn't care, but it's a special chord, Genesis. I need to specify that
DF perpendicular to AB.
and I'm going to say it's perpendicular at E. So now is where I'm going to mention the point E. DF is perpendicular to AB at E. Chord AC is not special. The fact that point K, I don't know that I need to specify anything about that per se. Now, they had to in what they told you, because otherwise you wouldn't know how to draw the picture. I really don't need to mention anything, though it wouldn't be wrong to say chord AC intersects DF at K. That wouldn't be wrong, but I'm lazy. It's not really anything special necessarily. Now, back to what we were trying to prove, Chris. What were we trying to prove?
AB times AE equals AC times AK.
All right, once you got that down, 2 columns, statements, reasons.
This is like those math problems that we did where it was what was segment times segment or whatever.
Product of the segments equals product of the segments. There's an analytical thought. We've got intersecting chords. Maybe there's something we could do with this. Given circle O with diameter AB, DF is perpendicular to AB at E. But before we get to all of that, let's think some clangy thoughts here. And Kendall, any clanginess that you notice?
Diameter.
All right, what's the clang of a diameter?
Semicircle.
All right, so we could specify that.
ADB.
Arc ADCB? Or in your case, by the way, you might have your AC coming down here, in which case yours would just be ADB. In my case, it's ADCB.
And chord AFB.
Arc AFB or AFCB.
Semicircle.
Reason?
Definition.
Ooh.
No. Diameter. Divides a circle into 2 halves and 2 semicircles.
Good. A diameter divides a circle into 2 semicircles. So let's go and say we've got some semicircles. That may come in handy. Audrey, clangage. Perpendicular. Thoughts? Right angles. So now I'm going to call this angle 1, 2, 3, and 4 because I'm really not sure what I'm doing yet. So I'm just going to go and get them all right angles. And so number 3. Angle 1, angle 2, angle 3, and angle 4 are right angles. Reason? I would venture to say, though, that the perpendicular here is more meaningful than simply right angles in that I have a diameter and a chord perpendicular. Not just 2 chords, not just 2 lines, but specifically a diameter perpendicular to a chord. Clangy thought there, Chris.
Bisects.
Bisect. If a diameter is perpendicular to the chord, it bisects the chord and
the chord and the radius.
Who help in class?
The arc.
The arcs that it intercepts. So number 4, we've actually got 3 different things that are being bisected here. You said, first of all, Chris, the chord is bisected. So let's specify that AB bisects DF. But it also doesn't just bisect the chord, so comma, AB bisects DF. What else does it bisect, Jamie?
It bisects the arc DCBF.
Arc DCBF. And So it bisects the chord, it bisects this arc,
Or DAF?
and the other arc, DAF, the major arc. Yeah, let's go and get all of that down. I mean, we're not sure what we're doing with this proof yet, so let's get the full power of the theorem here. Now again, if it were a radius, Jamie, you only have the chord and that one major arc. But with the diameter, you get with the one minor arc. With the diameter, you also get the major arc in there. So let's go and get all three parts here, because a diameter a diameter perpendicular to a chord bisects the chord and its arcs. Well, that just created a whole nother set of clang for me. Genesis? Bisects. What does it mean to bisect? Two equal halves or two equal parts, right? So if DF, first of all, is bisected, staying with you, Genesis, if DCBF is bisected, yeah, and if DAF is bisected, reason? Good, definition of bisector. Got a lot of clang. Any other clang that we can see? Any other visible clang? Ethan?
I don't think so.
Yeah, I feel like that's probably pretty good for now. I've got some right angles, I've got some semicircles, I've got some bisected arcs in the chord, which gives me some equal parts. Let's think analytically now. And Chris gave us an analytical thought right off the bat. He saw product equal to product. Say, well, we know if chords intersect each other, product of segments equals product of segments. So let's see what we've got here. This chord intersects this chord, correct? So I know that the product of AE and BE has to equal DE times EF, correct? And I also know because AKC and DKF intersect each other that AK times KC equals DK times KF. But we're not trying to prove either one of those, are we? We're trying to prove that this whole chord is to this piece, as this whole chord is to that piece.
AB is to
And these two chords don't even intersect each other. They just meet up at A. Yeah?
why don't we do AB is to AC as AE is to AK?
AB is to
AC
AC.
as AE is to AK.
Oh, okay, so you're saying instead of trying to find a product equals product, let's make a proportion out of it. Because if the product of two quantities equals the product of two other quantities, either pair of values may be used as the means, the other as the extremes. How many thinking that thought? Some of you also thinking that. So you said, what proportion was it again you were thinking?
AB is to AC as AE is to AK.
I think you said AK is to AE last time, but I could be
My
wrong.
bad.
Which would be correct, because these need to stay together,
Yep.
and those would need to stay together. I mean, that's the last thought we had didn't work out, so this is probably a good thought. How to make that happen? Let's go to Ethan.
Say more triangles?
Okay, triangles. Okay, Jamie. His thought was triangles. Does that make sense to you? Okay, you know what he's talking about. What triangles are we talking about?
A, B, K, and A, C, E.
All right. Now I don't have either one of those triangles.
Auxiliary line.
Okay, we could draw some auxiliary lines. What lines?
You could draw. Wait a minute. You could draw CE and KB.
Like that? We could do that. Anyone have another thought? Any other thoughts?
I don't know, but I don't
Is there an
know.
easier way than that?
I don't know that it might be a little bit easier way than this, possibly. I'm not sure if it's actually any steps less. Here's a thought. These triangles cross over each other kind of weirdly, don't they? And that can be a little bit annoying, couldn't it? Especially considering, let's look at ABK for a minute. Do y'all see ABK? See that this angle here is an inscribed angle. Do you see that this angle is not an inscribed angle? Because it doesn't have a chord. And you see that ABK or AKB is not made up of intersecting chords. So I don't know anything about B, and I don't know anything about AKB.
We only have one angle, because one angle is equal to A and A equal each other.
Okay, so Ethan's already observed, if you use these two triangles, you're going to want to say A equals A, but there's no way to do anything about the other angles. That's really obnoxious, isn't it?
Angle 1 equals angle 2.
Angle 1 equals angle 2. Well, that's true, but neither of those angles is in one of those triangles, right? So, yeah, I think that we may, like through some piecing stuff together, we may be able to make that work.
It'll be like 14.
But I don't really like those triangles. Is there a way to get different triangles?
Mm-hmm.
Thoughts?
Why don't we do, instead of ABK, or why don't we flip AE and AB?
Alternate, you mean?
Mm-hmm.
So here's the thought. What if instead of AB and AE, we had said AE and AB by alternation? Well, that changes the triangles. Maybe those next triangles would be a little bit more friendly, because those triangles didn't look too good, right? So that's okay. Alternation can give us more options. So let's see if this option's any better. If it's not, well, we'll go back to the first way. So now what are the triangles we're concerned with, Genesis?
Triangle AKE.
AKE. Okay, that triangle's right here. I don't have to draw any auxiliary lines. That's kind of a fact in its favor.
If you draw the line from C to B.
And ABC? And see now, class, you see I've got a little triangle that is formed by intersecting chords. Here I've got actual chords forming the triangle. That's probably going to be a little easier. Does that make sense? So let's roll with this adjustment. So we want to focus on triangle AEK and triangle ACB. We want these two triangles. All right, so that means we need to draw BC, which is what Genesis said to do. So Genesis, we'll go and write that in here. Draw BC. Reason? All right, let's get Kendall. Kendall, thoughts?
Those two triangles similar.
Right, if I can get the triangles similar, then I've got a proportion, then I can get that. Okay, so how?
Angle equal.
Okay, how?
Angle A.
Right, just once again, we've got this triangle, ABC, and we've got this triangle, AEK, and they both have angle A in them, right? So still we can use what Ethan mentioned a moment ago, that angle A equals itself. Reason, Kendall? All right. Audrey? Angle 1 and angle C. Okay, thoughts on 1 and C, Audrey? Yeah, because Kendall earlier had stated we had semicircles, angle C is inscribed in the semicircle, making angle C a right angle. Number 8, angle C is a right angle. Reason, Audrey? Good. An angle inscribed in a semicircle is a right angle. And then, Jamie, because C is a right angle, and we'd earlier stated that 1 is a right angle.
We can say they're equal.
We can say they're equal. Number 9, angle C equals angle 1, Jamie.
All right angles are equal.
All right, Quentin.
Triangle ACD is similar to triangle ABK.
Reason?
Angle.
Angle, angle. So there's number 10. Reason, angle, angle. And you did get the lettering correct. Good. A and A, of course, have to line up. The angle at C and the angle at E have to line up. And that leaves B and K to line up for the ending spots. So, good. All right. And once we've got that, Ethan,
Yeah, we just put state proportion that we have as number 11.
all right, reason.
Product of the regions plus.
Oh, how do I know that these similar triangles have these sides AE to AC as AK to AB?
Proportional. There's proportionals for some of the triangles.
Right, sides are proportional because they're in similar triangles in 5 letters class.
CSSTP.
Oh, yeah.
Corresponding sides of similar triangles are proportional. And then Chris, how do we finish this out?
AB times AE equals AC times AK.
Right, because
CSST.
no. That's what we used to get
Oh,
the proportion.
the product of these segments equals product of segments
How about product of the means
equals product of the extremes.
equals the product of the extremes. And there we go. All right, questions on that proof?
I feel like we just wasted a crap ton of time because I feel like we could have done this a lot faster.
Could we have done it faster? Well, let's see. I didn't actually end up using the bisector, did I? And I didn't end up using the equal halves, did I? But that's because we saw fit to alternate. Had we not alternated, let's take a look. Let's go back. What if we'd gone with those original triangles? Okay, I'm not sure that it works, but in my quick looking it over this morning, I thought I had it working out of here. Let's see if I'm right. I had this angle needing to equal that one there somehow. And the hard part is, again, I don't actually have intersecting chords. Obviously, this angle here is formed by intersecting chords, but this one's not. So this angle cutting off this arc is actually relatively meaningless. Unless could extend it out there somehow, but then it's equal to this and that piece of unnamed size. And then this angle here, again, has this right angle and this piece that, again, doesn't necessarily cut off that arc. So, no, I don't know that that would have worked. I guess if instead of going for the right angles, I'm trying to think back what I did, because I felt like I used it in the homework. If we had not gone with the right angles, there's your auxiliary line again. We could have said the angle C, or for that matter, angle B. Let's just say angle B. Angle B could have been equal to our half of arc ADC, and we would have had to also then go with angle K, which would have been half the sum of its arcs, DC and AF. But we could have said AF equals AD by substitution. Yeah, it probably would have taken a lot longer. So I'm glad Kendall got the semicircles. Okay, had she not gone with the semicircles, we couldn't use the right angle stuff, but then we would have needed to use this. Yeah, doesn't hurt to stay in good review for us if nothing else. Questions, comments on the proof? All right. Go and get out a new sheet of paper, maybe the back side of the paper you were just working on. And let's take a look at number 7, same section. Number 7 there in that same section. And go ahead and read number 7 for us, if you would, Jamie.
From the vertex B of the inscribed isosceles triangle ABC, a chord BE is drawn, having the base at D. Proves that AB squared equals BD times BE.
Interesting. Alright, so this time, our inscribed triangle will actually be, class, isosceles. And we're so tempted to assume isosceles-ness with these, and this time it really is. So go ahead and draw yourself, to the best of your ability, an isosceles triangle. And it names the triangle ABC, but it says that B is the vertex. So when you draw it, you've got your two equal sides, make sure B is the vertex going down to A and C. Now there's one more line we draw, Genesis. We also draw
Chord BE.
chord BE. How should I draw chord BE? Genesis. Any way I want? As long as it starts from B? Not quite. I can't draw it over here, or here, or here, because it has to cross the base AC at point D. Should I draw it perpendicular, class? Don't assume perpendicular. So I also shouldn't draw it so it bisects the angle or anything, but let's draw it kind of either closer to A or closer to C, Genesis. Closer to A. Let's draw it so it clearly doesn't bisect the angle, nor does it bisect the base or be perpendicular, anything weird like that. There's my chord BE, and there's my point D. And I think that's all we needed for the picture. We could name the center of the circle, I suppose, and let's name it Q, just to mix it up a little bit. And what do you suppose we should write for the given here, Ethan?
Circle Q. Circle Q. With inscribed triangle ABC.
Let's say inscribed isosceles triangle ABC.
With chord BE intersecting at D.
Is it doing anything special though? So probably don't have to state it as a
Unless it's
given.
bisecting.
But yeah, but definitely, yeah, good. Not bisecting, just intersecting. AC at D. We could state it, we don't have to. Now what were we trying to prove again, Jamie?
We're proving that AB squared equals BD times BE.
Interesting. The square of one leg is equal to the product of the segment to the base and the entire chord. Interesting. All right, once you got this down, 2 columns, statements, reasons.
So that's not Pythagorean theorem.
It is not Pythagorean theorem, you're right. You got circle Q,
That's what they wanted us to think it was.
inscribed isosceles triangle ABC.
The Pythagorean theorem can only be used on right angles, right?
Correct. Unless you have a right triangle, you can't use Pythagorean theorem, and we specifically made sure to draw it so it did not appear to have a right angle here. So, yeah, Pythagorean theorem's out, but it does kind of start out looking Pythagorean-ish. There's a big time clang in the given.
That's what I saw.
Isosceles. And what's the clang response to isosceles? Kendall?
Equal angles or lengths. Yeah. AB equals BC.
Reason?
Definition of isosceles triangle.
Good. AB equals BC, definition of isosceles triangle. That is in itself clang. Chris?
Angles. Angle C equals angle A.
Good. The opposite angles are equal. So that becomes clang in itself. So we've got equal legs because it's isosceles. Then those equal sides or legs give us equal angles. Number 3. Angle A equals angle C, reason, Chris?
Angles opposite equal, sides are equal.
Angles opposite equal
In a
sides
triangle.
in a triangle are equal. But there's another clang from number 2. Anyone?
Angle B equals
Chord
angle
AB equals chord BC.
Right, that's what we stated in number 2, is that these two chords were equal.
Angle, arc.
Arcs.
I meant to say
So
arc.
number 4, I thought you probably did. Number 4, Jamie.
Arc AB equals arc BC.
Reason, Jamie.
Equal chords. I can't remember the word that we use.
How about
Subtend.
if in a circle, if comma, in a circle, comma,
Chords are equal,
two chords are equal, comma,
then their arcs will be equal.
then their arcs are equal, or the arcs that they intersect are equal. Then their arcs are equal. But because I'm lazy, I don't want to write the word intersect. All right, if in a circle, two chords are equal, then their arcs are equal. All right, so we've got some equal arcs here. Let's see, any other clanginess? Clangage.
Inscribed?
What?
Inscribed?
Well, inscribed means we've got inscribed angles, right? We could definitely talk a little bit about those, but I think we might be getting a nudge ahead of ourselves if we do.
So there isn't more. Maybe we
So-
should switch to analytically or not analytically?
Yeah, I think we're ready to look at what we're trying to prove here. I think we've clanged it up enough. Quentin, looking at what we're trying to prove. Thoughts? We've already ruled out Pythagorean theorem, despite maybe our initial leaning. This squared equals this times that.
Confused.
Yeah. Have we ever seen anything like this before? Yes, we have. In our very last proof that we just did. They just didn't put a squared in there. But what does squared mean,
AB
Quentin?
times
Or times itself.
AB times itself. So really, truly, this just means AB times AB equals BD times BE. So thoughts, Quentin?
AB has to equal BD or BE.
I'm trying to prove that these two things multiplied equal those two things multiplied.
AB is to AB as BD is to BD.
Oh my.
That doesn't seem.
Audrey? Okay, what kind of proportion are you thinking? AB is to BD as BE is to AB. Now I will throw this thought out there, Audrey. Anytime you're given a quantity squared, we generally would make that the means to have a mean proportional. This isn't necessarily called an extreme proportional, but it's essentially what you do. Doesn't really matter though, does it? Because if this is true, I don't care that it maybe doesn't look the way we normally would write it with the means being equal. It's still going to give us this, right? So yeah, get a proportion. Back to Quentin, did that help? Sorry?
Auxiliary line, draw AE.
Draw who?
AE.
AE. Why are you thinking let's draw AE?
Good triangles.
Okay, which triangles?
ABE.
ABE, this whole thing here with the auxiliary line drawn,
ABD.
and ABD, this little guy here. So this little piece will actually be proportional to this whole thing there. So let's go ahead, number 5, and take Quentin's suggestion. Quentin, what was that again?
Draw AE.
And reason, obviously.
2 points.
And go and draw AE, because 2 points determine a straight line. And Quentin's thinking, let's get triangle ABE similar to triangle BAD. Though Abe was honest, he wasn't bad. But anyway, the people in the South kind of thought he was. They didn't like him too well. Anyway, he's rehashing old history. Y'all seeing the same triangles Quentin was talking about? All right. Thoughts, Genesis?
See if they're similar, but AA or something.
Yeah, AA or something. Usually AA. That's usually what we go with. Okay, so if we're going to go AA, we got to have some angles, right? What angles?
B.
Okay, angle B.
Both triangles share B.
Right, both triangles share B. Once again, we can say that angle B equals itself. Identity. And obviously not all similar triangles share an angle, but it sure seems to happen a lot with these pictures. I guess in a circle there's only so many places you can draw lines from. We need another set of angles though. Thoughts, Genesis?
They share angle A.
Well, not entirely. The one triangle that with the auxiliary line has this angle A. And the other triangle only has this original portion of A. So no, the A's aren't going to be equal to each other. Which means that the A right here has to equal something else.
E?
Yeah, because we said that the B equaled itself by identity, and you were looking at the little a, that's in the bad triangle. It's got to be equal to something else, and if it's not equal to A, the only thing left is the E. Now, obviously, that means we're going to need to change our lettering a little bit, but somehow I would need to get this angle E equal to this angle A. Everyone see that? Okay, thoughts? Genesis. What kind of angles are these?
A is an inscribed.
Right, A is an inscribed angle, so we know A would be half its arc, which is BC. What about E, though?
And it's going by a chord.
Oh,
So inscribed
it's also an inscribed angle, okay.
equals half AB.
Equals half of A, oh, AB. Okay, so A is half of BC, E is half of AB.
Very cool.
Oh yeah, AB and BC are equal. So let's go ahead and write down, Genesis, that angle, now I called it angle A earlier. This was before AE existed, so I'm going to call it BAC. Angle BAC, you said is equal to
Half arc BC.
half of BC. And you also said, on that same note, that angle E, and there's only one angle there, is
Equals half of arc AB.
reason?
And inscribed angle equals half its arc.
An inscribed angle equals half its arc. And so, because BC the arc and AB the arc earlier was stated as being equal, that means, Ethan, you said,
Angle BAC equals angle E.
reason?
Halves of equals, right?
Good, they're both halves of equals. So, halves of equals are equal. And there we go. I've got my angle, so my triangles have to be, class, similar. Now, Audrey, I'm going to come back to you, Because I think you mentioned the triangle. No, it was Quentin earlier. Quentin had mentioned the triangles. Quentin, how exactly should I put the letters in the right order here? Okay, so triangle BEA is going to be similar to triangle BAD. And of course that reason for number 9, class, angle, angle. Once we've got that down, back to Audrey. Good, or you could switch the means with the extremes, make these the means, so you have a mean proportional, but it's fine even if you don't. And the reason, Audrey, for number 10? Right, once triangles are similar, you know, corresponding sides are proportional, CSSTP. And then once we've got that, Jamie.
Then we can say the AB squared equals BD times BE.
Good, because?
Because products of the means equals product of its.
And there we go, in 11 steps. Questions on this proof? Questions on this proof? We don't have time to do this last proof I wanted to do, and it's number 3, so I just want to talk through the proof with you. Number 3 at the bottom of the page. Go ahead and read that for us if you would, Kendall.
Prove that if two circles are tangent externally and through the point of contact is sinking strong, the chords formed are proportional to the radii of the two circles.
All right, so we said we have 2 circles are tangent externally. What does that mean for circles to be tangent, class? They touch at one point. And tangent externally means that both circles are separate. All right, so we have something like this. They have one point in contact with each other. And it said, Kendall, that if we have 2 circles tangent externally, that if
The point of contact, a secant is drawn.
through this point any secant is drawn. Now, if I went straight across, we proved earlier in the year that straight through the line of centers would go through the point of tangency. I don't want that chord, I want some other secant line that's going to cut through this point, okay?
The chords formed are proportional to the radii of the two circles.
So we're going to call this point of tangency T. Prove that the chords are proportional to the radii. So if I call this circle O and this circle Q, there's radius OT, there's radius QT. And we would say that the chords AT is to BT, AT to BT, that's proportional to OT to QT, the radii. The thought here would be this. First of all, normally when we get lines proportional, class, we would have some are triangles, but I don't have triangles. Thoughts?
Auxiliary ones.
What's your auxiliary lines?
OA and BQ.
Okay, OA and BQ.
Vertical angles are equal, so we have one side.
Now, this would be the first key. This line of centers has to pass through the point of tangency, and that's something we had proven. If that's true, then we have 2 straight lines, not 1, 2, 3 straight lines meeting at a point, correct? Which would make vertical angles equal.
Angles at O and Q are equal. Well,
How do we know the angles at O and Q would be equal?
proportional. That angle at O equals arc AT.
Right.
Angle at Q equals arc BT.
Right, but those arcs aren't equal, are they?
It'd be proportional.
Are AT and BT the arcs equal? They're not even in the same or congruent circles necessarily, right? Thoughts? Anyone? Are these radii, stay with me, are these 2 radii, OT and QT, equal? No, for sure not. What is equal to OT? OA. What is equal to QT? QB. Thoughts?
Isosceles triangles.
Isosceles triangle, so therefore
Equal angles.
angle 3 equals 1, angle 4 equals 2. But if 1 and 2 are equal, then by substitution, class, 3 and 4 are equal because they're equal quantities. So there's my angle, there's my similar triangles, and there we go. So that's how we would have finished out that proof. We just didn't have time to actually do it together. Your only homework this evening, don't forget, finish up that handout. Hopefully you're about halfway through or more, because otherwise it's a 3-page handout. But finish up the handout. We're going to go over it tomorrow. Again, that handout, if you're watching on YouTube, was in the description of the previous lesson, lesson 146. Test coming up Friday, lesson 151. Have a wonderful rest of your day, and you are dismissed.